So thank you very much for the invitation to this workshop. It's really exciting to be here. And I will talk today about learning manipulation skills from instructional videos. And just to illustrate what I mean by instructional video, here's an example. So imagine now you have a flat tire somewhere where it's not easy to get help, but you do have access to your, on your phone to internet. So you can Google, how do I change car tire? And you can get a video which looks something like this, where a person is showing you and explaining to you how to do these different steps, how to use these tools to change the color of your car. So there is both visual and language input. And in fact, if you don't like that particular video, you can find there are several other videos which maybe with different tools or different car types. But in fact, there are really millions of these instructional videos online, which in different domains, from car repair to cooking or gardening or even healthcare. So really, they provide a sort of wealth of information where people explaining how to achieve a specific task. So we thought, well, wouldn't it be great if we could really learn from this data? And the vision is like, what if we could really extract automatically from a video some kind of an instructional manual, so that one can then use that sort of automatically use that instruction manual to automatically give instructions, for example, via an augmented reality device, how to do a novice, how to do a specific task, or in a sort of industrial environment, how to maybe even check that the assembly task is done correctly. Or, and that's I think what's relevant more here in this workshop, how to use that information for sort of teaching robots, how robots can learn from instructional videos, how to achieve specific tasks, and maybe then execute them in new environments. And so in this talk, I will sort of show you some of our work in this direction, and sort of covering four different domains, starting with learning visual language representation on a large scale, and then moving more towards extracting sort of, or having models which are more grounded in the 3D sort of geometry and physics of the real world. And finally finishing with our sort of initial steps towards having sort of visually guided control. But I will do most of the talk, I will focus in these two middle parts. Yet I wanted to start to really illustrate what one can get from these videos on a large scale. So the initial work which we did on this was really extracting the sequence of steps from instructional videos. So which are, and I'm just showing you the result here, where on the right we have the extracted steps automatically using the vision and language from a small number, from a set of maybe 50 videos of a specific task. And at the bottom is the localization, the temporal localization of these steps in the video. When we were doing this, we realized that there is only so much one can do on this small scale. So that was our motivation for really moving large scale with these instructional videos. And then we discovered this website, which you may know as well, called WikiHow, where you can really search for how to do almost anything. So what we did, we queried that sort of curated from that website a set of 23,000 different tasks. So a task would be, say, how do I make a cocktail, for example. And the only curation which we did was really that these tasks should be visual. So people talking about things which they do in the video, rather than more abstract topics like how to fall in love, which are also contained, but we removed those from the set. So we ended up with 23,000 different tasks and more than 1 million videos, which can be really long, maybe up to even 10 minutes, where people describe these different steps, which we chopped up to smaller clips, maybe about 10 seconds, and obtained more than 100 million these short video clips with narration, which we can transcribe using automatic speech to text. So we have these snippets of visual and language information. And really sort of on the scale of the data sets in visual and in video and language, this is one of the largest that is available. There may be now one which is sort of large, even a bit larger, but you can see that it's really sort of 3 orders of magnitude bigger than most of the existing data sets, which are usually manually curated. So the difference here that we don't write the captions ourselves for these videos as most of these other data sets, but we use this automatic speech to text. And really what we explored, well, can we learn these video language models from this data? And this is usually formulated as a sort of contrastive learning task where the goal is to given a video and a caption, like here, you can see, we learn a video model, which is usually a neural network, and a language model, also neural network based, in such a way that the videos, the representations of videos and the associated captions are close in that space, and videos and captions of different videos are far. So this is usually served as this contrastive learning. And so these type of models are, recently have been shown very successful in the image domain. And here in the video domain, they also work, as I will show, but there is this additional difficulty that we have to deal with, is that these captions are not necessarily perfectly aligned with the actual video, because people may be talking about things which they will do in a future, sort of in maybe next minute. So there's this additional noise in an alignment problem which we have to deal with, and we've developed models which can deal with those issues. So I will not go in too much detail into this. I'm just putting the citations, but instead show you some of the results. So this is an example of, so we end up with a model where we can really query, put a language query and find videos back by searching close by videos in that space. So if you type glue, this is what you get back. So people are, so clips of people gluing stuff. Now, but if you type glue wood, you suddenly start getting videos where people are gluing pieces of wood together. When you type cut wood, people are cutting wood. And these, you can really compose these more, put cut paper, you see videos where people cut paper, but even if you put cut paper in circle, you get video clips where people are cutting paper in circle. So this is very exciting, because instead of really having to define a vocabulary of labels of actions, you can use the natural language and its natural compositionality to define really a fine-grained sort of labels, which are label space, which is very large. And just to show you, one can quantify this also. So this is on the y-axis is a performance of this text-to-video retrieval. So how accurately I can retrieve given a query, for a given query, I can retrieve the video. So this is the percentage of time I retrieve the correct video. And you can see on the x-axis that the performance improves with the larger the data set I have. And this is the case for several downstream tasks. You can see in different colors here. And for one of them, this is a particular data set of cooking videos with light blue. There is this dashed horizontal line which shows the performance of a fully supervised model given the manual annotation on this data set. So you can see that with this automatically trained model on this large scale how-to data set, we can eventually outperform, if we have enough videos on this text-to-video retrieval task, a model which is fully supervised with the annotation in the video, which there's a smaller amount of them, but they are sort of curated by people. So with a scale, we can eventually, which is very exciting, that we can outperform the fully supervised models. So the code for this is online for these papers and demos. And I also want to show you just a glimpse of the very recent work where we use this large scale how 200 million data set for training models for video question answering, where the goal is given a video clip and a question like what is in the blue plate. The model has to answer, provide a language answer, which in this case is butter, which is correct. And there are some results here. Here's another example, which the difficulty is that for this task, there are different types of questions on actions, on objects. So here you can see a correct answer of our model for an action query. Here is an example of an object query. So one can adapt then these representations for different and use this type of data also for different downstream tasks. So what I've been showing so far is training large-scale models on this data, but these models were linked to natural language, but they were really not really grounded in the geometry of the real world. We couldn't really extract like so if you want to say use those models to teach a robot, this is not quite there yet. These models don't even localize yet well in the image itself. So in another line of work, we also looked at, on a smaller scale so far, we looked at extracting more sort of geometric information from the video. So this is given a single video, instructional video from YouTube on the left. The goal here is to extract the 3D trajectory of the person together with the 3D trajectory of the tool, which the person is manipulating, the hammer here, and estimates of the contact forces, which are here shown as yellow arrows between the person and the ground and the person and the object. So this is the goal of the goal here, and we formulated it as this two-stage process. Then the first stage, in what we call a recognition stage, where we sort of measure a 2D information from the image, like the skeleton or the position of the object in the image, together with the contacts, which was an important component, like which joints are in the contact with the ground or the tool, which then simplify the following estimation stage. And then in the estimation stage, we estimate the actual trajectory of the person and the tool in 3D. Just to show you, here are some examples of the 2D measurements extracted from the video. Another example here, and I will be coming back to this example later. So given these 2D measurements, we then formulate the estimation stage, we reconstruct the motion. We formulate as an optimization problem where the goal is to where we optimize over the state of the system X here, which is the skeleton of the person together with the object endpoints in 3D. We optimize over the control of the system, which involves the contact forces and muscle torques, and the 3D position of the contact points on the ground along the tool. And we minimize a cost function, which is really kind of a reprojection error, so that when we project the estimated 3D trajectories into the observed videos, we can sort of explain well the observed videos with the 3D trajectories. And this is here, so this is sum over time, and also here sum over the human and the object. So we have a loss, this kind of a reprojection error for both human and the object. And this is all subject to the constraints of the sort of physics constraint of the contact motion model, full body dynamics, and a force model. We have sort of tested on 2 data sets here. The first one is more to validate it as on this data set where we have ground truth motion and forces from motion and force sensors. But what's really exciting is that this other part where we have the data set of these instructional videos where we can extract, as shown here, this is the input video, these are the 2D measurements, and these are the extracted, estimated 3D motion with estimated forces from 2 different viewpoints for several different actions. And I will show you just a few more of these results here on this data for a few different actions. As the hammering. So this data set has 5 different actions and so several videos of each so manipulating the tool. And so when we saw this, we think, well, wouldn't it be great if you could then use this information to transfer the motion to tool motion onto a robot? Can we somehow use this to then use the video to drive the robot? And this is really the next project of PhD student Katerina Zorina, who is actually giving a poster on this work in this workshop later. So if you want to know more details, please talk with her. The poster. I will just give you a few-minute overview of this project, which we are very excited about. So here is given the input video, and this is one of these videos which you've shown from YouTube, which you've seen earlier. And on the right is the output, where this is really a policy executed on the robot, which is sort of transferring again, material from one place to the other. And now what I will give you is a sort of a bit more details how we actually do this. So the input to this approach is we have the input video together with a simulated environment, which contains the tool and is a sparse reward, in this case, about transferring the material from one place to another. So this is given as input on a sparse reward with the environment and the video. And then we have sort of three-stage or three-step strategy to learn a robot policy for this task and then transfer that policy onto the robot. And I will now explain these three steps. The first one is extracting the 3D trajectory of the tool from the video. And for this, we use the approach which I've just explained, where we estimate the trajectory of the person together with the tool. So we estimate both the person and the tool, but in this approach, we really use only the tool. So we kind of forget the actual motion of the person and only keep the motion of the tool. Yet estimating the motion of the person was important to really get the tool directly, because the perception algorithms, the computer vision, the recognition is not good enough at the moment to really give the trajectory of the tool by itself for these kind of thin objects like the shovel here. So the estimating the trajectory of the tool together with the person is important. But now for the transfer to the robot, we forget the person and only keep the trajectory of the tool. And I will show later that this allows us then to easily transfer this motion to different robots. But now we have the trajectory of the tool. And the next step is to align the simulation environment with the video. So here, the goal is to find the scene layout of these different elements in the environment that maximize the reward, the sparse reward of the trajectory which we've extracted. So we have this trajectory extracted from the video of the tool, and we are now, the goal is to find the arrangement of these elements in a way that we maximize the sparse reward of transferred material. And of course, this is a hard optimization problem because there is a huge space of possible layouts. So the idea which we have here is that we guide the sampling. So we sample these configurations and we guide the sampling by the extracted tool trajectory. So we extract kind of a key points along the trajectory and use those to guide sampling of these scene elements. And the output of this is that maybe this is not an optimal, is very likely not an optimal trajectory, but it's a trajectory which transfers some of the material, obtains some reward from the environment by aligning these the environment with the video, with this extracted trajectory. And the next step after this is to actually learn a robot policy. So the output of the previous step is the trajectory of the tool without the robot. And in this case, in this step, we would like to actually learn a robot policy that still the same goal, to maximize the sparse reward. We found that directly applying reinforcement learning on that setup was difficult. Sparse reward is very difficult. And even using the tool trajectory just using directly RL was difficult. So the approach which we are taking is to imitate the tool trajectory using trajectory optimization and then fine tuning using RL. So we really formulate the problem as a optimization problem where the goal is to output the optimal joint velocities and the position of the robot, which is fixed, and joint velocities at different steps of the trajectory. And the cost which we minimize is the distance to the demonstrated trajectory. So you would like the robot to imitate the trajectory well, extracted from the video, to follow the trajectory of the tool extracted from the first step. The subject, there is a velocity regularization, joint limit constraints, and of course, subject to the robot dynamics so that the velocities respect to change in robot configuration. And this really gives us an initial trajectory of in the robot space of the joints, which imitates, which sort of imitates the tool trajectory. And then, and for the optimization, the heavy lifting is really done in the optimization by these two tools, Pinocchio and Crocodile, which we found to work well for this. And finally, we optimize the final, the sparse reward using reinforcement learning, which is fairly standard. I will not go too much in detail of this. So with this policy, the apply to the robot at the moment is applied in a feed-forward manner. So there is no visual feedback at the moment. So here is just some results. Here we have a data set, in this case, 3 tasks, spade, hammer, and sight, and 5 videos for each task. For each of these tasks, we have an environment we designed with a sparse reward, which is in this case transferring material, hitting hammering a nail, and an environment for cutting grass. We do have in the paper quantitative evaluation, but I think in interest of time, I will skip it at the moment and show more this experiment, which I thought was quite exciting, where we actually use the same algorithm, same approach to transfer to different robots. And we can do this because we really we don't worry about the human here, only about the tool which we extract. And then we use 3 different robots into simulated environments and end up with 3 different policies with the same algorithm. We can end up with 3 different policies depending on the robot configuration. And again, here we can evaluate the reward on the y-axis for different robots and obtaining very much similar rewards for different robots. And this working much better than the sparse RL with the sparse reward, which is shown as the red column here. So, these were sort of initial results on being able to, from an instructional video, go all the way to a policy executed on a real robot. Yet this policy is feed forward, which of course is a demonstration. It can be done, but ideally to have a robust execution, one would like to have a visual feedback. And towards that, so we don't quite have results really on demonstrating the visual guided control, but in order to go in this direction, we have developed already an algorithm for 6D or accurate object pose estimation. So if you want to manipulate objects and give sort of visual feedback during execution, we would like to understand where the objects are in this scene. So this is an example of the input image, and this is the example of the output scene. So in this case, we know the 3D models of these objects, and we can estimate their poses in the scene, so that given now, say you want to grasp an object like this, we can recognize the object in the scene, estimate its 3D pose, and plan the motion. So the 6D pose estimation problem has been around for a while. So we've designed an algorithm which combines powerful neural networks with multi-view constraints, and it's all trained from synthetic data. I will not go into details in this, but show some of the results where for single input image, these are the predicted poses in the middle image here, and the visualization of the 3D scene at the bottom. For 3 different scenes. These are all estimated from a single image. So these are some of the standard data sets for this problem. And this method works even for objects which are self-similar, like these similar cups here. And it does work very well. There is a challenge associated with this problem, 6D object pose estimation, and this approach has obtained very good results, outperforming some of the other methods and reaching accuracy of methods using depth information, whereas this is only RGB based. And finally, before I conclude, I just want to mention that we also extended this work. So what you've seen so far was rigid objects, but we've extended it also to articulated objects, so that here, this is input video on the left, and on the right is estimate of the 6D pose and articulation of, in this case, the articulated object is the robot. So one can estimate not just the camera object calibration, but also the actual articulation of the object from the video. And this is done independently on each frame, so not using the temporal information. And with this, I would like to just conclude that this is an exciting time to be in, where we see more integration of perception, learning, and control in robotics. We are approaching more from this perception side, but we are excited, and we have collaborators more on the robotic side to integrate these results together in robotic systems. And with this, I thank you very much for your attention.